Is Assalamualaikum and very good morning. So welcome to Embedded Processor System SKEL4663. So in this chapter, we're going to look at processors and also high-level language programming for embedded systems. Okay, so this is chapter number 2. So what we're going to see in this chapter is actually okay. So the objectives of this chapter is actually to learn about the different types of processors and their differences. And also understand the high-level language compilation process. We're also going to look at the GCC compiler toolchain, and we're also going to run some commands on the Linux environment, which is normally used for many embedded systems out there. So let's look at some of the different types of processor. The first one is the embedded processor. Okay, so for this, what we have is a processor that executes instructions sequentially. And the set of instructions that it can execute, which mean the instructions such as add and multiply and divide and so on, we call that the instruction set. Okay, the ISA. Okay, instruction set architecture. Okay, and of course, different processors, they will have different ISA. But we can basically classify them into two different processor or two different architecture types. One is what we call as a reduced instruction set computer, and the other one is actually the complex instruction set computer. Okay, and so these are the different types of architectures we have. In reduced instruction set computer, we have simpler instructions. Okay, we have simpler instructions. Okay, so that these instructions can execute faster. But even though we have simpler instructions, what we're going to get is the CPI, cycles per instruction, will be low. However, our instruction count will go up because we don't have complex instructions. Okay. The advantage of simple instructions is also that we can actually have a higher clock rate. Okay, we can have a higher clock rate because we can create the pipeline stages to become shorter and shorter because our instructions are actually simpler. In complex instruction set computers such as the Intel x86 processor, the cycles per instruction is a bit higher. Okay, but the instruction count will be lower because now you have complex instructions, but you do have challenges in actually getting higher clock speeds. Okay, because the processors are a bit more complex, which means it will take longer time, and if you want to do pipelining, then it will be more challenging lah. Okay. So these are the different instruction architecture types. So for example, your ARM processor that you have today in your mobile phone is actually a RISC processor, but with added complex instructions as well. Okay, so you can't really truly find a pure RISC processor or a pure CISC processor today. They are normally actually a mixture of both, having simple instructions and or having a processor with what we call many registers and simple instructions, or perhaps with an addition of complex instructions too. Okay, so but traditionally we can divide our processors into two categories. One is reduced instruction set computer, and the other one is the complex instruction set computer. You can also buy microcontroller. So what you have used so far is the AT Mega 32, which is also available on the Arduino board, right? So this AT Mega 32 is a chip that falls under the category of microcontroller. Okay, so on the chip itself, so there's a chip here. Okay, so on the chip itself, what you have is actually a processor inside, the CPU inside. You also have some I/O. You also have memory. You also have flash memory and so on. So everything is on the same chip, same IC, okay, same integrated circuit. So this is actually what we call a microcontroller. Of course, we have an 8-bit microcontroller. We also have a 32-bit microcontroller, a 16-bit microcontroller, depending on what kind of application you have. But basically, it's just as an IC with a CPU and all the necessary things inside the same package. Okay. For things which are more complex, you may need an embedded controller. So for example, you may have a controller for your engine control unit. Okay. or you may have a controller for your what we call in-car entertainment. Okay, so you may want to have a more complex controller, or more powerful controller, because your application is more complex. So for this kind of application, you may want to go for something of a higher performance. So we do have that. For example, the ARM microprocessor has several series for targeted for microcontroller application. We call it the M series. We also have certain series to target real-time application, the R series. We also have several chip that targets the more complex application, the application series. So the ARM processor has several series for different applications. It's just like the Intel processor, you have the Core i3, the Core i5, the Core i7, and then you have the Core i9, depending on what kind of performance you want. Uh, Another manufacturer for embedded control is such as MIPS. So MIPS actually make processors that as normally you will find them in smart TVs and things like that. Okay, so these are some of the types of embedded controllers out there. In some problems, you may just want to use a desktop processor. So you have this Intel processor or an AMD processor, and you want to use in your embedded application. For example, you have an ATM machine, or you may have what we call a billboard, a digital billboard, a big billboard by the roadside. Okay, you have a big billboard by the roadside. Okay, near the road. Okay, so you say there's an advertisement here. Let's say Lazada sale, for example. Yes, you may have a big billboard. You want to have a controller for this, for driving the LEDs and stuff like that. So if you want to use a general purpose processor, it's also possible. You can just use the processor available on the shelf, such as the Core i3 or the AMD processor for your application. So it really depends on what kind of application you are actually targeting. Obviously, if you want to drive a big, what we call LCD display like that, a big, what we call um, this notice board here, for example, you can't really use a Arduino board. You can't really use an 8-bit microcontroller because it's just too slow. It doesn't have the required peripherals to do that. Okay, so it really depends on the application, but you have the choices of going all the way from microcontroller to embedded controller and to a higher performance general purpose processor, depending on your application. For some application where the target is real-time signal processing, you may want to go for DSP processor. So you'll find this DSP processor in your phone a lot. So you may have an iPhone, for example. Okay, so inside the iPhone, you'll find this, let's say ISP, image signal processor, or you may find a DSP, digital signal processor. So these are actually processing these what we call pictures coming from your lens camera going into ISP, or maybe your audio when you're speaking through the microphone going to your DSP to be processed. So you may find these special processors for certain application where you need to have a very tight processing time and very specific application. Okay, so ISP and DSP are examples of a DSP processor. Okay, in your laptop you'll probably find this GPU, and your phone also you'll find a GPU as well. Besides your CPU, you have multiple CPUs. You'll also find a GPU. So the purpose of GPU is very specific to do graphics. Okay, and in your laptop you'll find something like an Intel graphics card, or an AMD Radeon, or a NVIDIA's GeForce card. So these are all actually processors specially designed for the domain of graphics. So this is very good at just doing graphics. Okay, of course, it's not to be used for general purpose. You don't run your Microsoft Word on top of your GPU, but for the drawing of Microsoft Word, or for the rendering of whatever you see on the screen from Microsoft Word, is done by the GPU. Of course, a GPU can do even heavier tasks such as rendering 3D graphics. For the domain of graphics, you have a special processor for that. Sometimes you may need a application specific instruction processor, or ASIP. This is a tailored for specific application. So you may have a specific application that you want to accelerate and still programmable. Okay, then you may have an ASIP. Okay, so let me just demonstrate to you one of it. So let me go here. So let me see, for example, Canon Digic. Okay, so this is one of the processor by Canon. Okay, So the DIGIC or digital image integrated circuit or DIGIC processor is a family of signal processing control units and for digital camera and camcorder. So we have a special IC for that. Okay, so this special IC is used in Canon cameras, especially like this DSLR. So the latest is 11, I think. Okay, so we have this some digit 6, digit 7. Okay, so this is actually used in the phone. Sorry, in this camera to do this image processing in real time. So this is actually application specific processor. Okay, special for their camera only. Okay, it's not to be used somewhere else. They design a special processor to accelerate the things that happen in their DSLR cameras. For example, capturing HD videos, capturing burst mode, doing image processing in real time, doing auto focusing, things like that. So they do that inside this application specific processor. Okay, you can see that what you can do is that it can perform image quality, it can perform what other things, high speed processing, face detection, and stuff like that, all inside that chip. All right. We also have FPGA. So I think maybe I've gone for some Verilog class or HDL class where you use FPGA. So FPGA is basically a circuit, okay, where you have unconnected gates inside, okay. And you can actually download a circuit written in hardware description language such as Verilog or VHDL. And when you download this description of the circuit, okay, for example, you describe an AND circuit, you describe a decoder, you describe a multiplexer, or you describe something more complex like adder and multiplier, or even more complex a CPU. Okay, you describe it in a hardware description language of your choice. And what you do is that you download the circuit to this FPGA board or FPGA chip, the field programmable gate array chip. So the configurator is going to build the connection to represent that hardware description. So if your hardware description is an adder, an 8-bit adder, so the hardware in this FPGA will be connected to represent that 8-bit adder, for example. Okay, so what you're going to get is a digital circuit on the FPGA, which is very, very fast. The good thing about FPGA, it is reconfigurable. And then the other thing is that you can build your own circuits in parallel. So you can do parallel processing. And then it is application specific. You can do whatever you like. You don't have to, what we call, you don't have to buy a special processor to do image. You can do your own image processing algorithm and then download it to the FPGA board. And the circuit will be downloaded there, and the FPGA will be configured to do whatever you want. So in other words, rather than build your own circuit yourself, you can program the FPGA chip to represent your circuit. So that's the advantage of what we call FPGA board. Okay. All right. So some of the available FPGA CPU core. Okay. So you can see that FPGA is the chip, right, with some pins and so on. You can always program the chip to become a CPU if that's what you want. So if you want to have this CPU on this FPGA board, we call this as a soft core. Okay, so some manufacturers, they provide an available soft core for their FPGA chip. For example, they sell you FPGA chip and you need a processor design in it. So they say, okay, we also have a soft core for the processor. If you ever need a processor in your FPGA, you can just program it with our soft core. Okay, so these are some of the available soft core processor name from different manufacturers. For example, Microblaze from Xilinx, Neos and Neos 2 from Altera or Intel, okay, and Leon from Spark and so on. Okay, so these are some of the common or available soft core for different FPGA platforms. All right. So let's keep this one first. So now let's have a look at what is a system on chip. Okay, so what we have here now is that we have an IC, okay, which is not only a processor, okay, which is not only a processor. Okay, so inside the IC we have CPU. So we have a central processing unit or many CPUs. Sometimes it's a dual core, so you have two CPUs, and then we have a controller for your peripherals such as a USB, for example. Okay, and then we also have, let's say, a GPU inside the same IC. We have image signal processor, we have a DSP, we have a video decoder, and so on. So what we have is that we have an IC with a complete system in it. Okay, a complete system on that chip. So we call that system on chip. Okay, system on chip. So rather than have many separate components, okay, many separate components in your system, you have one CPU, and then you have a memory controller outside, and then you have a GPU separately, and then we have many components separately. Instead of having that, we bring everything together in a single chip. Okay. So this is the kind of idea that we have. So inside the same chip, we have things like computational engines, data processing engines, memory, peripherals, all inside the same chip. So this is just an example. You have a speech codec, SRAM, and then you have a digital to analog, analog to digital, and CMOS camera. What else? A RISC processor, a DSP processor, and so on. So everything is inside the same chip. So later we can have a look at some commercial chips out there and what they have inside the chip. Okay. So when you have a system on chip, it's just not a processor. Okay. So when you pick the chip, this is not a processor. This is a system on chip. So inside the system on chip, we have many components. Plus we have a processor. Okay. So a processor is just a component in a complex system. All right, so what we have on the left side here is what we call a system on board. That is the traditional way of doing things. We have this motherboard here, okay, the PCB here, the motherboard here, and we have several components on the board. And now today what we have is we integrate all these components, or at least as much of it, into a single chip. So you may have a single chip with memory, peripheral, DSP, microprocessor, a microcontroller, microprocessor, ASIC, a specific IC, ADC, DAC, everything in a single chip. Okay. The reason why we want to do this is because we want to get a faster performance. We want to get a more compact design. We want to have a design security so people cannot steal your design or people do not know what is your magic formula inside. And then what else? We can have because we have a very good process technology. That is, we can now fit millions and billions of transistors in the same, let's say, 1 millimeter square, for example. So in the same space, now you can put billions of transistors. So that makes it possible for us to bring many IC or many IP into the same chip. Okay, it was not possible before because we don't have that process technology, or we don't have that density available to us, and then that's why we can't actually integrate everything in one IC, but that is now possible. Okay. So what do you find inside a typical SoC? What you'll find is maybe several one or many cores of processors. Could be homogeneous or could be heterogeneous. Homogeneous means that the processors are same. Okay, so for example, in my laptop, I have 4 processors. They are the same. Okay, they are the same processor inside the laptop, so same capabilities, same clock rate, and so on. Or maybe you may have something like heterogeneous. So in heterogeneous, such as in my phone, I have 8 processors actually, or 8 cores, but 4 of them are big. Okay, and then we have these 4 high-performance processors. Okay, high performance, but then I also have 4 tiny processors for low power mode. Okay, so we have 4 tiny processors. So in this case, the configuration is actually heterogeneous, which means we may have many processors, but they are not the same capability. Okay, we have a big one and a small one in the same IC. And the reason we have that is because when you play games, you want high performance, so we use the high performance CPUs. But when your phone is not ideal, the phone is idle, and you're doing chatting and you're doing simple web browsing, If you turn on the high performance processor, it's going to consume too much electricity, too much battery, too much energy, too much power. So we use the smaller chips. Okay, we use a smaller CPU core for tasks that are not that does not require high performance. So this one you'll get a good balance between what we call performance as well as and the energy saving. Okay, so you get the best performance of both. Okay. um, of course, in the SoC, you may have some specialized functional units. You may have co-processors. You may have GPU and DSP. You may have memory. You have some sort of bus architecture, peripherals, and also these are the kind of things we have in a SoC, and we can have a look later of some examples of it. Okay, so let's have the first example here. So this is a generic diagram of an SoC. So example, right? So we have a power and clock coming from outside. We have a boot, flash memory, and DRAM outside. Okay, but inside the system on chip, what we have is timers and interrupt controller, the CPU itself, some cache memory that is connected to some memory controller, and then we have some communication protocols for peripherals. Okay, so that's an example of a system on chip. Okay, I have many more examples after this, so let's have a look at that later. Why we want to do SoC? The reason is because, like I said, we have a very good process now. Okay, so we can fit billions of transistors, so now it's possible, which makes it cheaper. Also gives you better power consumption. You can make faster circuit because everything is tightly integrated. Smaller size because everything's on a single chip. You don't have to make a PCB and then make the design bigger. More reliable because everything's on the same IC, so you have less points of failure in the system. And like I mentioned, it's design security. No one knows actually what's actually happening inside your IC. Is pretty much mysterious. Okay, people can inspect, but they can't really get the exact idea of actually what's actually happening inside. So it gives you some sort of design security. So in order to achieve this SoC, what you have is what we call a platform-based design. That is, you don't design a chip from zero all the time. Okay, what we want to do here is that we want to get IPs, that is intellectual properties. What is intellectual properties? Means the different components you have inside your SoC. So for example, I need a USB capabilities and I need a 4G modem in my system on chip. Okay, so I don't really have to design this. I can always purchase this from a company X and purchase it from company Y, and I integrate that inside my SoC. So this makes my design process faster. Okay, so for common processors such as memory controller, USB controller, USB on the go, HDMI controller, 4G modem, 5G modem. So I don't really have to design everything. I can always source the design, or we call it the IP, from someone else and pay them, of course, and then use them in my product and integrate that in my system on chip. For example, 5G modem, not everyone makes 5G modem. Samsung and Huawei and Nokia and some other companies do make it, but not all the companies, they have the strength, they have the capabilities, or they have the knowledge to come up with a very good 5G modem. So instead of doing it yourself, what you can do here is that you can source the IP from someone else. Okay, and that's a good thing. You pay the licensing fee, or you pay whatever the royalty you have to pay, and you get that IP and you integrate in your system. Yeah, so you don't have to spend money designing it, spend time, and then it will not take a day to design. It takes some months, right? So you don't have to spend time and money on it. You just have to buy it from somewhere else, and then you just integrate in your system on chip. Okay, so that gives you faster time to market. Reuse, that is, if I have different series of CPU, okay, Snapdragon 800, Snapdragon 600, Snapdragon 400 series, three different series of the processor or the system on chip, but all of them requires a 4G modem, so you don't have to redesign over and over again. You can just reuse that IP in different designs. Okay, and then when you can do this, you can actually add your customized value. Okay, where is your actual value? Your value is not in USB controller. Your value is not in the 4G modem, but perhaps something else inside your CPU. Sorry, inside your system on chip. Maybe a very good image processor that makes it makes your chip very good. So when you take a photo, it gives you excellent photo quality. That's where your focus is, rather than the common things like USB and 4G modem and stuff. So those things you can always acquire from somewhere else. Okay, so the design goes like this. You can do a complete ASIC from complete logic, okay? But this gives you a problem in modifying. So when you modify, you have to completely redesign it over again. Or you can have a very tightly integrated IP inside your ASIC. This makes it difficult for you to do plug and play. But a platform-based approach is that you can actually swap in and out these IPs with minimal, or you still have to do some integration, but it's not going to be as complex or as difficult as a tightly integrated ASIC, or even as a completely customized logic. Okay, so in this case, it will be much simpler, much faster to do the integration. And should you change it, for example, you want to change to a different processor core, then you still have to do the work to integrate it, but it will not be as complex as other approaches. Okay. So what kind of IP blocks that you can acquire? You can get processor. Obviously, you need a processor from ARM or MIPS or PowerPC or Spark and many more. You may need to interface to the outside world using USB, PCI, UART, and stuff like that. You may want to provide some sort of encryption for your applications. You can get a DES, AES, and other encryption techniques. You may want to have a video or MPEG decoder, for example. Okay, you can add that decoder and encoder, networking, special DSP processor, and maybe you want to have some support from real-time operating system. So these are kind of the IP that you can integrate in your chip. Okay, so let's have a look at this Snapdragon. So Snapdragon is one of these famous chip nowadays, right? I think the latest one is a Snapdragon 888. That's the latest processor. Okay, so let's have a look at this image. So this is Snapdragon 888 with a 5G modem inside. So if you look at this diagram here, hopefully I can get a bigger picture. Yeah, that's the big picture there. A rough picture, they show it like this. You have a one big Cortex X1 high performance CPU, followed by three middle range A78 CPUs, then followed by four smaller efficiency CPU. This is, we call it efficiency CPU, a low power CPU targeted for when you don't quite use your phone very heavily, so it will switch to these low power chips. Okay, and then what else you have? You have this cache and system cache. Any other information? Yeah, is it the same one? Yeah. This is this 888 has also inside the 88 you also have a Cairo CPU. You see, this is your SoC. Inside SE you have the CPU and many other things. So let's just focus on the CPU because inside this one you have the CPU, you have the fast connect, you have this is CPU, you have what other things. I'll try to find another diagram in a while. Okay. So what do you have inside the CPU? You have okay, this is the chip lah. Okay, you have the CPU here, right? So inside the CPU you have 25% performance and so on. But what else you have? You have image signal processor, you have a GPU, you have a hexagon processor, you have a sensing hub, you have a security chip, you have a 5G modem, you have a fast connect modem system, and so on. So what do you have inside your GPU? You have a GPU for processing, video processing, display processing. Anything else? What about the connector? You have this is ISP image signal processor for 4K. You also have a Wi-Fi modem, a Bluetooth modem. You have ISP again. You have a quick charge IC and so on. So there's a lot of things inside the chip. Can I find a much better diagram? Or maybe we can go for the spec. Okay, let's have a look at the specification. So it says that inside this SoC, the 888 5G SoC, that the chip here, inside that you have an hexagon processor, and the hexagon processor contains an AI accelerator. Okay, and then you also have a 5G modem called the Snapdragon X60 5G modem. Then you also have a Spectra image signal processor. Then you also have a Qualcomm Snapdragon Elite Gaming thing, I do not know. Then you also have a Wi-Fi 6 chip inside. And then you also have a Qualcomm processor security with TruePic. What else? So you have a lot of things. If you read here, the specification, you have a lot of things. You have a Adreno GPU, you have a CPU, you have a hexagon processor, you have a voice assistant, you have a vector extension, you have a modem, you have an AI enhanced signal boost. This is for the modem. And then you have LTE. This is for the 5G modem. You have a Wi-Fi chip inside. You have a Bluetooth chip inside. You have a near field communication chip inside. You have a GPS inside supporting all of these things. You have a USB controller. You have a fast connect. You have a Spectra image processor. You have a codec support. And so many things. So there are so many things on the SoC. So the processor is just a small part of the system on chip. Then you have so many other things on the system on chip. Okay. So that's what you have to realize. You just don't have a processor. Just for your phone, for example, when you buy a phone, it's just not just a single processor. You have so many other things together with it. Okay. This is from Intel Atom SoC system on chip. The model number is Z2580. Just an example here. So here you can see it's a single IC. So this is a single IC. Inside this IC, we have a CPU. Then we have a level 2 cache, we have a DDR memory controller, we have a 2D, 3D graphics controller, we have a video decoder, video encoder, I don't know, display control pipeline, video image enhancer, ISP image signal processor, there's a bridge in it, there's a crypto engine, and then we have some IO for DDR2, SD card, HDMI, UART, and so on. SPI again. So this is a single system on chip with so many things inside. The CPU is just one small thing in it. What about this one? This is Z3000 series. Okay, so here you can see here we have two memory controller for dual channel, power management IC. Inside the same system on chip, you have image signal processor, Intel GPU, video decoder, display controller for DisplayPort, eDisplayPort, HDMI. We have one CPU core, two CPU cores, three CPU cores, four CPU cores, so 4 core, and then 2 megabyte of level 2 cache. And then we have other things here as well. We have GPIO controller, boot ROM, legacy controller, SPI, UART, I2C, PWM, SDIO, SD card, eMMC, USB on the go, USB 3, USB 2, I2C, audio engine, and this is I2S, is for sound. Okay, this is I2C here. This is I2C. This is for other communication. Okay, I2C. So different. This is for audio. This is not for audio. So a lot of things inside a single system on chip. What about this Quark SoC? Is very small. It has Intel Pentium 4 processor actually, the quad core here, and then we have the SRAM, DDR3 memory controller, JTAG, clock, PCI Express. Many other things I do not know here. I think this is SPI. No idea, no idea. ROM. No idea, no idea, no idea. RIM tile clock. GPIO. SD card, UART, GPIO, I2C, SPI, Ethernet, USB 2. Okay, so a lot of things on this system on chip. All right. Okay, so I think that's all. You want to start with okay, so I can start this a bit lah. Okay, so now let's have a look at high-level language programming. So in your degree so far, you have seen this high-level language programming in C programming class in your first year, and also your microprocessor class in the previous semester, right? All right, so I just want to have a quick poll. When did you take your microprocessor class? I mean the 80 mega 32 class. When did you take it?
Last sem.
Last sem, huh? Okay, so most of you, if not all of you, have taken it last semester, right? Yes. As Ahmad Izzuddin says, third year, which is what? Last year? 2 years, 2 semesters before? Ahmad Izzuddin? Last 2 semesters means between the previous and the previous semester lah. So 1 year ago lah. Okay, it's not actually 1 year. It's actually 6 months ago, right? 6 months ago you took this C programming class, right? Okay, just give me 1 second. Okay, all right. So Tai Jing Wen says 2 semesters ago, not the last. Some say last semester. If you say last semester, which means 2 weeks ago, right? Because the last semester ended 2 weeks ago. You did the exam like a month ago or 3 weeks ago. So, which means, of course, you studied until the exam, right? So, 3 weeks ago was the last assessment for your embedded for your microprocessor. For the ones who took 2 semesters ago, which means 6 months ago was the last exam, right? 6 months ago, you did the final exam for 2 semesters ago, right? You started 2 semesters ago, but it took you 6 months to go through the semester, and then you then attended the exam, right? Which means your knowledge is fresh 6 months ago. Okay, okay, great. So let's continue. So in this class for embedded system, you're going to use high-level programming, which is C. Why we're going to use C is because it's very efficient, just as efficient as assembler. Of course, if you write all your code in assembly language, it's going to be very, very efficient. The problem is that writing in assembly requires you, even for simple processors, you have to write very complex thing. Okay, for example, I just want to add 20 numbers. So in assembly, code will be very long and you can make a lot of mistakes. And if you're not good at assembly, you may create a very slow code as well. Okay. So C programming is kind of a high level. You don't talk about registers. You don't talk about the specific instructions on the CPU. You just describe in high level language. Okay. So C programming language is fairly efficient. And not only it is high level, it still supports the ability to access the low level IO. So that makes it very flexible. And the other thing here is that um, there's a lot of open source code available for C, whether it's Linux or anything else. This makes it very flexible for you to develop your application or your product. If you write your code in assembly, then it is only targeted to that chip. So if I write a code for ATmega32, which you have done maybe in last semester, and now I want to bring the code and run it on my Intel processor, the assembly code will not work, okay, because the assembly code is targeting this processor only, this ISA only. But if you were to write the code in C, then with minimal changes, now the code can run on different platforms. So that makes it very portable, okay? So this is some of the things that you have already known from your microprocessor class. So this would be easy. How can you do I/O in C? How can you change bits in C? How can you do pointer arithmetic? So all of these things you have done in your microprocessor class. Okay. All right. So a very quick review. Okay. Uh, last 3 semesters. Okay. Never mind. Still you have studied already. That's the important thing. Okay. So this is the basic architecture of your C code. You have your comments here. You can write your comments this way. And comments are actually ignored by the compiler. If you want to include a separate file in your current file, you use this hashtag include. Okay. So this hash means a preprocessor directive. This is actually done by the preprocessor before compilation process. So this is actually telling the compiler to include or bring the file into this file. This one is also a preprocessor. It's telling this compiler that whenever you see the word port base, replace it with 0x4000, hexadecimal 4000. Okay, so these are actually preprocessors. And then on top of your C code, you may have a definition like this, where you have a function definition only without anything else. So we call these prototypes. Okay, we call these prototypes. This is just like an index in a book. Okay, so if I have a book with me right now, for example, okay, this is a book with me, a statistics book. So when you open the book, you're going to have this table of contents, right? You have this table of contents on what page you have what. So these prototypes is actually a table of contents. Okay, the reason is because imagine if I don't have this. Let me delete this. Okay, imagine my program is just here. So when I start my program at main, suddenly I find my function. So the compiler is going to throw an error because the compiler will say that you have never declared my function. I do not know what is my function. Is it a variable? Is it a function call? Is it a definition? I do not know that because I've never seen it, right? Why? Because my function is not here, because the compiler will compile line by line. So my function has never been seen before. In fact, my function will appear later down there in the program code. So in order to introduce that to the compiler first, we put it here. We call this a function prototype. So when the compiler compiles from top to bottom, it will see this first and it will say, oh, okay, there is a definition for a function called my function. So later when I see my function, I know it's a function call. So when the compiler compiles it and when it sees this, it will say, okay, this will be replaced by a branch to my function. Okay, what is the address of my function? Don't worry, I will resolve this later when I reach my function. So the compiler can put a placeholder, okay, a placeholder, so that you say, I will fill up the address later when I reach to the point where I know the address of the function. Okay, but I know it's a function because I've seen the definition first. So the function prototype is for that. And then we have this main function. So every C code must have a main function. Okay, that's 99% of the time you must have a main function. Okay, so this main function is where your program actually enters. So when you start your program, it will enter through this main function. Okay, and then of course you can have any other functions that you want. Okay. All right, so if you have seen this before, your embedded program normally runs forever. So even on your 80 mega 32, you will start from somewhere and then you have a branch and then the program will repeat itself, branch to the main program, repeat forever until you press a stop button or anything. It's the same thing with the embedded controller. So if I have an aircon controller, it will run forever. It will check this room temperature. It will check the set point of your controller, and then it's going to compare. If the room is hotter than what you want, then it will start the compressor, and then make the room cooler, and then it's going to measure the temperature again and repeat and repeat and repeat. So it runs forever. So what you will find is in most embedded programs, you will have a loop, a big loop called while one. While one means true, or you may have a for loop with nothing inside. So this will spin forever. So this thing will spin forever. Okay, so you may find something like that in embedded program. Of course, there's a lot of logic going inside your program. So this is again just a revision. The if is only checking for a condition that is true inside. So if the condition is true, it's going to run the if block. If the condition is false, it's going to run the else block. Okay, so what is a true? A true is anything that is non-zero. So any value that is a non-zero is considered true. That includes 1, 2, 3, or true, the Boolean true, -1, -2, -85. Anything that is non-zero is considered as true. Okay. So let's have a look at this one, some expression. So in this case, a is greater than 3. So if the value of a is greater than 3, this will become true. This will become true and the block will be executed. What about this one? There's an AND operation in the between. So if A is greater than 3 and at the same time B is equal to 2, then when this is true and this is true, true and with true, everything becomes true, then the block is executed. What about this one? If 1 is always true, so this block will always run. What about if 0? This is always false, so this block will never run. What about this one? This is also useless because 3 is true, 6 is true, you all both of them is always true. What about this one? A equals to 0, which means that if A is 0, so when if A is 0, 0 equals to 0 becomes true. 0 is equal to 0, so it becomes true, so it will get executed. This is a not operation, same like the top here. This is wrong. This is assignment rather than comparison. This you can also do this way. All right. What about some bit manipulation? So let me stop here. Okay. Let me stop at this slide. What about bit manipulation? So you've done this also in your microprocessor class. So for example, we have A and B here. This is given A and B. A and B means for every bit you perform the AND operation. So 0 AND with 1 is 0, 1 AND with 1, 0, 0 AND with 1, 0, and so on. That's an AND operation. What about an OR operation? OR means OR, 0 OR with 1 is a 1, 1 OR with 1 is a 1, 0 OR with 0 is a 0. So it's a bitwise. So we call this a bitwise operation. So we do bit by bit. This is an XOR operation. This is a shift left by 1. So you can see this is A, right? A, this is A. Shift left by 1. So this will go out, this will go here, 0. This will go here, 1. This will go here, 0. This will go here, 1. This will go here, 0. This will go here, 1. And this will go here, 0. And then you feed with a 0. So 0, 1, 0, 1, 0, 1, 0, 0. So 0, 1, 0, 1, 0, 1, 0, 0. Okay, so this is shift left by 1. Shift right by 2. Complement. So this is complement. So 1 become sorry, this is B, right? 0 becomes 1, 0 becomes 1, 1 becomes 0 is just a complement. All right. Okay, so I think that's enough for today's class. In the following class, we are going to install VirtualBox. So you can download VirtualBox from virtualbox.org, and you can download Ubuntu Linux, which is going to be approximately 2.7 gigabytes. Approximately it is 200 megabytes from the internet, and we are going to run our Linux operating system there, and also our GCC compiler inside Linux. Okay, so I'll see you in the next class on Thursday with you having downloaded VirtualBox and Ubuntu Linux. All right. Thank you very much. If you have any questions, you can ask. Otherwise, the class ends here.